This is the first of three segments talking about bottom processes, part of the bottom processes lecture. In this one, we're just going to go through some of the basic properties of sediment. Key thing about these bottom processes, we have an interaction between the hydrodynamics and the sediment. And the hydrodynamics are including both wave-driven and current processes or velocity processes. We have a boundary layer, and that boundary layer is flowing over a relatively uneven bottom, imparts a stress on the bottom, and that stress can give rise to erosion of the bed, transport of sediment, and those sediment processes shape the bed, and the bed itself can have some kind of roughness. And in the lower left figure down here, you see roughness imparted biologically by scallop shells, and here you see ripples that are created by currents and waves flowing over the ocean bed. And that roughness can then feed back and influence the shape of the boundary layer flowing over the bottom. So the two interact. It's not a one-way process. Why are we going to study these? Well, we have a lot of contaminants that get trapped in the sediment, and the Bedford Harbor is a classic example of this. And the fate of the contaminants is linked to the transport of sediment in and out of, say, an estuary or a harbor. We have filter feeders that live on the bottom, and some of them live in a relatively harsh environment. And their ability to filter is influenced by the flow velocity, and the sediment transport is also influenced by the flow velocity. So you have this relationship where if the sediment transport gets too strong, the filter feeding shuts down. They're unable to basically exclude the food from the particles using their normal mechanisms. Also in new settlers, very young of the year, they settle, they're small, they have difficulty keeping themselves from being buried, and so there's these sort of mortality events associated with strong storms, typically wave storms that can suspend and move a lot of the seabed and bury the young of the year. Another important factor, particularly these days, is looking at the impacts of gear on the seabed. You really have to get the natural setting in terms of what are the impacts, the daily impacts from tides and wind and waves on the seabed in order to determine whether a seabed impact from man-made, from gear fishing, is big or not. It has to be compared with the natural environment, which influences the recovery time following a fishing event. Sediments are heavier than water, so if you drop a grain of sand in the water, it will settle to the bottom. The density of sediment, most of them are made of quartz, and the density of that is about 2,650 kilogram per meter cubed, so it's about 3 times or 2.5 times the density of seawater. They're classified in a number of different ways. A very common one is what's called the Wentworth scale, which divides up sediments into different groups: clays, silt sands, cobble boulder, as well as some intermediate groups such as medium sand, fine sand. And these are all determined simply based on a diameter or a characteristic diameter, because none of them are truly spherical. If you see this collection of grains here, you can see some of them are rather oblong, sharp on the edge, and that actually affects their ability to pack together and slide against each other in a rather complicated way. The other is the phi scale, and it's related to, here's phi, it's related to the diameter d. It's the log base 2 of the diameter, where a diameter is expressed in millimeter. It's also negative, such that the phi scale gets more negative as the diameter gets larger. We can also express the diameter in terms of phi here. It's 2 to the minus phi. The phi scale is a natural scale to use because the way these sediments are normally determined, the distribution of sediments in the seabed, is you scoop up a sample and you sieve them. So you use a very fine sieve to sieve out the fine ones, and then you sieve you keep sieving the sample with coarser or larger and larger sieves in order to determine the distribution in each of the sieve classes. The sieves generally change by a factor of 2 each time, which is why we have this log base 2 separating the classes in the phi scale. The units on sediments are generally either millimeters, you see, or micrometers, occasionally nanometers, but typically millimeters, micrometers. Millimeters are more commonly used in riverine or coastal sediments, which tend to be coarser and are on the order of a millimeter. Whereas when you're dealing with muds and silts, those are closer to micrometers, and it's easier to work with those units. Micrometer being 1/1000th of a millimeter or 1/1,000,000th of a meter. This table just simply shows the relationship between the diameter, characteristic diameter, in millimeters, the phi scale, and the Wentworth size class. And you can see you start from the top. We're talking about boulders. You have roughly a meter scale, diameter, and phi -8, -12 range. All the way down to the sands in here. We have very coarse, medium, fine, very fine in the Wentworth scale, corresponding to phi classes from -1 all the way down to +4. And that corresponds to the diameter from about 2 millimeter down, 2 millimeter down to about 5% or 0.05 millimeter. And then you go to all very, very fine particles. You can see the range of diameter here, which is the physical dimension, is massive. We're talking about a massive range of particle sizes that we're calling sediment on the ocean floor. This is a grain size distribution. Typically a seabed, as we saw in the previous few examples zoomed in, aren't composed of grains that are exactly the same size. In a lot of places the range is fairly small. If you go to the beach, on the outer shore of Cape Cod, and you scoop up some sand in your hand, you have essentially coarse sand, or somewhere ranging from fine sand to coarse sand in your hand. And in that will be some larger grain sizes distributed among that in your palm, but they're fairly uniform. And we can determine this using a series of sieves and a shaker, which basically shakes the sand through the sieves, and use a sequence, as I mentioned, of sieves with larger and larger mesh size, going by a factor of 2. In doing so, you can produce one of these cumulative curves. So you start with your sample here, and you shake out the finest ones, and you set aside that mass, and then you shake out the next group, and you set aside that mass. So you're shaking out coarser and coarser grain sizes as you move to the right. You have the total mass of the system. That allows you to put this cumulative distribution in front of you. So at any grain size, for example, around here, about 1 millimeter, this is around coarse sand, I believe, you have that 20% of the mass in this sample is finer than that. So this is a fairly coarse mass sample, this particular one right here. A lot of the mass in the sample is made of coarser substrates. And if you move, so one of the definitions that is commonly used is D50. D50 implies that 50% of the particles by mass are finer. So here's D50, and it says, so that's exactly half the weight of the sample once we've shaken to D50, and half of that is coarser than whatever D50 is. In this case, about 3.5, or about 12 millimeters. It's pretty coarse, and half of it is finer than that. You also have a definition D84, which is related to a standard deviation of a standard distribution of grain sizes, but this is also a commonly used sample to establish the higher grain size. At D84 diameter, 84% of the grains are finer than that particular grain size. You also see D90 used occasionally, D10, some other definitions. Now, having two separate numbers, D84 and D50, allows you to determine how well sorted or poorly sorted the sample is. If it's well sorted and all the grain sizes are about the same size, then D84 and D50 are not going to be that much different. And you have that the ratio of D84 to D16 is less than 2. This is one of the definitions of well sorted. If D84 is much bigger than D50, that implies you have a wide range of grain sizes, as you see here. And in that case, you have the other extreme, which is poorly sorted, and in the beginning, or in the intermediate ranges, you have other values. These are not hard and fast numbers, but these are sort of back of the envelope calculations. Some key non-dimensional numbers associated with sediment transport. One is the critical shields parameter, which basically is a ratio of the hydrodynamic force that's going to be imparted on the sediment, and that is the critical shear stress, the shear stress needed to erode the sample out of the bed relative to the particle weight. The particle weight, so basically the weight of the sediment is largely trying to keep it in the seabed. And so these two things are fighting against each other to see if the particle is dislodged or not, essentially. That's a critical shields parameter. The second one is a type of Reynolds number. We've spoken about Reynolds numbers before in the semester. This is a grain Reynolds number, and by grain it implies that the length scale in the Reynolds number is the grain diameter, d here. So you have a characteristic velocity, you have a grain diameter, and you have the kinematic viscosity here of water, about 1 to the minus 6 meters squared per second. This is, again, as all Reynolds number are, a ratio of the inertial forces acting on this particle to the viscous forces acting on this particle. And this can influence, for example, the settling velocity. And then you have, the last category of this dimensional is grain size. This is commonly used in many of the sediment transport relations. There isn't an official sediment dimensionless grain size. Sometimes you see this third, sometimes you don't. So you have to be a little bit cautious about that. But this relates the particle Reynolds number and the particle weight. And as I mentioned here, there are other definitions of this D star, so just be cautious. But it does include the ratio of densities between the sediment and water. Again, that's about 2.5. The kinematic viscosity here, and the physical diameter size here. So we're trying to create a dimensionless diameter, and that's what that does. None of these things have units. They're all unitless parameterizations. These particles fall, and again, the general balance is between the shear stress from the water and the waves trying to suspend or keep these particles and get them out of the bed into the water column, and the weight of the particle, which acts to pull it back down into the bed. And those two things are fighting. So key thing is what is the rate at which a particle settles down from the water column into the bed. And essentially, a falling particle, we can think of it as a sphere, although as I mentioned, they're not spherical exactly, but we have a sphere falling in the water column, but they're very small. Primarily, these particles are very small, so they act at very small Reynolds number, and life at that Reynolds number is very viscous. We can ignore largely the inertial forces, and life to them is very different than it is to us or a whale or anything sort of large scale. Acting down, you have gravity, which is simply proportional to the diameter cubed, right? That gives you the volume times the density difference, because rho sed is getting pulled down and rho water is the buoyant force pushing back up. So the difference between them times gravity. And then you have the drag force, and the drag force is proportional to the diameter squared, the surface area, or you can think of it as the cross-sectional area. So all these drag forces typically we write as a drag coefficient times the density, times the velocity, times an area. In this case, the characteristic area that we use for a sphere is the diameter squared to set the drag coefficient. So drag coefficients are established using different characteristic lengths areas. For a sphere, we use diameter squared, and that drag coefficient depends on the Reynolds number. It's not a fixed number. And we have rho is the rho water. So there are many formulas to determine how quickly things fall. As you can imagine, smaller particles fall much slower than larger particles, and this is really the way it is in life. As we get bigger, as we increase our length scale, or in this case, the diameter scale, the weight of that thing is increasing much faster than the surface area. So the gravitational force is increasing much faster than the drag force, and so the terminal fall velocity is going to be much bigger, meaning we have to get to a higher W set in order for this thing, the drag, to compete with gravity. And this is the reason why you take an elephant, I'm not advocating this, but you take an elephant and throw it off a roof, and the thing basically combusts when it hits the ground. And you can drop a mouse, I believe, from any height at all, and that's because mice have a lot greater surface area relative to their volume, being smaller creatures, which means they have a lot more drag force relative to the weight that's pulling them down to earth. The same goes for the sediment in the water column. You can intuitively think you can drop a cobble, a skipping stone in the water, and it will drop much faster than a tiny grain that you might find on the beach, and that is true. So this just gives you some idea. For the Wentworth scale, we have very coarse sand, again a millimeter. That's a good number to remember. Very coarse sand's a millimeter. And you get about 64 centimeters per second. And you have 16 seconds. I need to check on that. I'm a little suspicious about that. This is time to get through a 10-meter water column and all the way down to clay. Once you get to clay, you can see the settling time is extremely slow. So the variation in settling speed or settling velocity, and if you think of a fixed distance, and settling time is humongous across the range of grain sizes that we experience on the ocean floor. So the sediment dynamics and what's going on in response to a given forcing is going to strongly depend on the nature of the materials that lay on the seabed. I did have one video I wanted to show you, but what I will do is wait for the, I'll show it to you now. So this is a video, hopefully it's not too cut off, excuse my poking around here, okay? I'll put the link up on the web, but this is a video taken of a stream bed. Now stream beds are typically pretty high energy environments. If they're coming out of the mountains, you have a large gradient in the elevation, which drives rapid stream flows. They're shallow, there's lots of stress, and they typically are carrying these larger sediments. Look at this underwater GoPro footage. You can see these sediments. Now there's two types of sediment transport that's going on here. One is what we call bed load, and that's these grains moving, just running across the bottom. See? It's like a sheet flow. You can see almost a sheet of suspended materials riding over the materials that are fixed to the bed. You can see the large materials, like this rock right here, are not moving at all. This rock is stationary. The flow is not strong enough to pick up that rock and move it. It looks like it is, but it's not. Here you see the camera looking directly into the sheet flow, which is a pretty great shot, actually. Again, this is bed load moving along the bottom. These particles are not in suspension. They're moving as bed load, rolling and saltating along the stream bed. Above it, if you look carefully, you'll see a cloud up here. See the silt? This is silt in the water. Hopefully this will slow down for a second here. You can see it here. It's a cloudy kind of mist in the water column. We can't see directly up into the blue sky because of this silt that's in suspension. So these very fine particles are also present in the flow and actually may have been carried from much further up. I don't see this much silt in this bed here. These silt particles, which appear as a cloud in the water here, could have been transported very far. Again, their settling velocity is so slow that once they get in suspension, the turbulence can easily keep them into suspension. The video says he's moving towards larger material. I'm not sure what that means. Let's have a look. Oh, there's some biological here. Rusted chain was once used to secure a floating seafood processing vessel. I'm not sure what that means. But you can see here, nothing here is in suspension. So either the bed stresses are diminished or everything here, as he said, is larger grain sizes. So we see nothing being suspended. And the bed load here is essentially zero.